Okay, so welcome back. Our first talk on this session on hexagonal compounds will be Megan Holtz from Cornell University.
All right, thank you for the introduction, and thank you to the organizers for inviting me here. Is my volume okay back there? Okay, so today I want to talk about mapping the ferroelectric order parameter in hexagonal ferroelectrics, going from bulk hexagonal manganites, such as erbium manganite, where we're going to look at the inner structure of ferroelectric domain walls and vortices, and then go further and see what happens when we dimensionally confine charged ferroelectric domain walls in this structure in epitaxial oxide superlattices. And so this work was done, the microscopy was done in David Muller's group at Cornell University. The superlattice thin films that you'll see later were grown in Daryl Schlom's group, and the erbium manganite was provided by Dennis Meyer in TNU. The DFT theory was done in Craig Finney's group, and we also had Landau theory with Andres Cano. And then we had a lot of characterization from Peter Schiffer's group and also from Ramesh's group at Berkeley. And so this session today, we're going to be talking about hexagonal ferroelectrics. And so these are compounds such as yttrium manganite or erbium manganite. And these are geometric improper ferroelectrics, where a geometric distortion in the crystal is generating a net ferroelectricity. So in this case, we have layers of rare earth 3+ ions with iron or manganese surrounded by bipyramids of oxygen. And what will happen is these trigonal bipyramids will tilt in the crystal, and this will create a rumpling of the rare earth ions, which then generates a net ferroelectricity. And so what you have in this sample is a Z6 symmetry breaking, where you have 6 ferroelectric domain wells. And this is, you have the 2 different polarization directions, the Z2, polarization up and polarization down. And then because this is a trimerization, this 3-fold symmetry breaking, you get another Z3. And this generates a lot of interesting phenomena, lots of topological defects, which we're going to hear about in our next talk. It also opens doors to coupling this kind of ferroelectricity with magnetism, which was talked about in this paper here. And so these types of ferroelectric materials open doors to different kinds of oxide interfaces in these ferroelectric domain walls. And so this is a scanning probe microscopy, CAFM, and you can see you have these 6 distinct ferroelectric domains wrapping around the single vortex, the single point, and then an anti-vortex on the other side where they're wrapping in the other direction. And because of these vortex structures, which are topologically protected, you get these domain walls winding through at random orientations running through the sample. And because they're going through the sample in this way, you can get interesting electronic reconstruction. So here you have a tail-to-tail wall in this erbium manganite, which is more conducting than the bulk. And over here you have a head-to-head wall, which is darker, so it's more insulating than the bulk. So you get these electronic reconstructions. You can also, due to the symmetry breaking at these domain walls, get other emergent properties. So here, this is still erbium manganite, but now at low temperatures, you can get magnetic moments appearing at the domain walls, depending on what types they are. And so just to really briefly cover, we have these types of ferroelectric domain walls. And most of the time in most crystals, you want to have these neutral domain walls where the divergence of the polarization is 0, so you have no charge buildup at the walls. But what's happening, because we have these winding domain walls through the crystal, we get charged ferroelectric domain walls pretty commonly. And here, the divergence of the polarization is not equal to 0. And so you get a buildup of charge at these walls. So here we have a head-to-head ferroelectric domain wall where the polarization is pointing at each other, tail-to-tail where they're pointing away. Also, and then these are the neutral domain walls where the polarization is parallel to the wall. And so at these head-to-head walls, you can get interesting electrostatic reconstruction. So here, erbium manganite stem image of a head-to-head wall. You can go and look by electron energy loss spectroscopy at the manganese L2-3 edge, And you can see that it shifts to slightly lower energies near this domain wall. If you fit that out to different manganese spectra, you can see that you get about 0.1 electrons per manganese ion accumulating at that domain wall. And that can give you some interesting effects. So here's this CAFM image of the erbium manganite at 2.5 volts. You can see you have the insulating head-to-head and the conducting tail-to-tail. Then when you apply a 6 volts at your tip, suddenly both types of walls are showing enhanced conductivity. So you can get this qualitative change in the electronic transport. And that's because as you apply this larger bias, you're dumping more electrons into there, and you're going from a more localized state to a more itinerant state. And so you can imagine making different kinds of domain wall devices with this. So this is like a ferroelectric domain wall switch, where you apply a voltage and you turn the switch on. But one of the things we're really interested to look at with this is, what is the structure? How does the order parameter change as you get close to these topological defects? And scanning transmission electron microscopy is a good way to do that. With your hat-off stem, you get the Z contrast, which lets you basically directly look at the displacements of these rare earth ions. And so from this, you can look at the top, and there's 2 ions in the down position and 1 in the up position, so it's polarization down. Whereas on the bottom, there was 2 on the up and 1 on the down, so it's polarization up. And this displacement that you can measure out in picometers here tracks monotonically with the polarization in microcoulombs per centimeter squared as calculated in DFT. And so we can directly pull out the polarization by looking at the crystal this way. So what we can do to measure the order parameters, we can also go atom by atom through this crystal, look at the left neighbor and the right neighbor. And then we can classify it into these 6 different ferroelectric categories, 3 for polarization down, 3 for polarization up. And so we can go one step further with this, and if we fit a sinusoidal curve to the displacements of these ions, we can directly pull out the order parameter. So here we have the amplitude of this displacement, Q, and also the phase, wrapping around this phase wheel phi, for these 6 different ferroelectric domains. And that can directly pull out this order parameter, Q cosine phi, Q sine phi. And so here are some typical images of domain walls in erbium manganite. So on the left, we have a tail-to-tail charge wall. On the right, we have a neutral wall. And then we can put a color overlay over this for the polarization. So here, in this case, blue is polarization up, and red is polarization down. And we can map the order parameter phi going across these ferroelectric domain walls. And so the thing we sort of notice going through here is that it's not abruptly changing in this case. We have a continual gradient going from 1 pi over 3 phase to the 2 pi over 3 phase on the right. And so what we can do is compare this to Landau theory and map the change in this phase as a function of position going across this domain wall and fit out this distance. And we get about 6 angstroms for this neutral wall and about 7 angstroms for the charged wall. And so this is sort of telling us that the domain wall width isn't determined necessarily by electrostatic effects, since the charge and the neutral are the same, but by the mechanical stiffness of the crystal. And this might be expected since this is a geometric improper ferroelectric. We can also look at the trimerization amplitude Q as a function of position on the wall, and we can see that this isn't changing that much. Slight change, but not much. So we can also go through and map tons of regions, take many images, hundreds of images of the different ferroelectric domain walls, and we can make histograms of what the order parameter is, Q sine phi, Q cosine phi, and we can pull out a physical measurement of the energy landscape going through this material. So you can see the ferroelectric domain switching is going from one domain to another, just like we would expect from the free energy landscape, which is shown here from this paper. We also see vortices in this material. So this is where all 6 ferroelectric domains are winding around a single point. And here we can see that it's actually going down to one atomic column in this crystal. So all 6 of the phases are wrapping around one single point. If we look at the amplitude here, what's happening as we go towards this core is that we do get a decrease in the trimerization amplitude towards the middle. It almost goes to 0, but it doesn't quite. And so we can look at the Q amplitude as a function of the radial distance from this vortex core. And we can see that it decays away at about 7 angstroms. And so what's probably happening here is that the ferroelectric domains are coming in, they have a finite thickness, and they start to overlap and kind of cancel out into this middle region. We can also look and see how the phase phi winds as we go around the vortex core. So when we're really far away from the vortex core, we have so this is the angle around the vortex and the phase. So when we're pretty far away, 6 nanometers away, we're kind of going in this stepwise function that you can see here. But as you get closer and closer to the core, and you're winding around here, you start to see that the phase is progressing in a pretty smooth line. And so we're going from somewhere where we have this Z6 symmetry to something where we have more of a U1 symmetry, this continual winding. And so here you can see from this cartoon that I've taken from this paper, these Z6 states. As you progress towards the TC, in this case, you get this U1 symmetry where it's rotationally invariant. And so the domain walls of this finite size are, again, starting to overlap as you get close to here. And this, So in this case, we were able to see this ferroelectric vortex. And in erbium manganite, this atomic resolution stem allowed us to measure the local order parameter changes, both going around these topological defects through vortices and domain walls, and also over the overall crystal to see what the measurement of the local energy landscape was. So from that, I wanted to move towards a different system. So now this is going to be lutetium ferrite superlattices. And this was a system that we started looking at to try to generate a room temperature multiferroic. And I'll talk a little bit about that. But in the process of that, we also realized that the structure was also confining ferroelectric charge domain walls. And so then I'll talk about how confinement affects these charge domain walls in a bit. Okay, so lutetium ferrite was a promising phase space to look for a multiferroic material. So we have on the right-hand side this hexagonal lutetium ferrite, isostructural to the erbium manganite we were talking about before, and it's this improper ferroelectric, which we hope we'll be able to couple to magnetism. And so this is ferroelectric up to pretty high temperature, 1,000 Kelvin, but it's a weak anti-ferromagnetic ordering with around T150 Kelvin. So above that, it's not doing much magnetically. The 124 lutetium ferrite, on the other hand, this material is ferrimagnetic around 240 Kelvin, and it has the same structure in plane, but instead of one iron layer in between here, we have 2 iron layers, which is letting us get this interesting magnetization. So we also have other reasons to believe that this lutetium ferrite might be interesting from a multiferroic perspective, which is you have this state here. This is the ground energy state of the structure, charge order 1. But if you displace it into this structure here, you add on some amplitude Q to this ferroelectric distortions. What you're getting here is as you increase this Q vector, you can push the TC up, because as you're doing this, you're reducing the geometric frustration of this triangular lattice in this material, which is then reducing your magnetic frustration and increasing your TC here. So as you turn on these ferroelectric distortions, you can get potentially above room temperature multiferroic material. So by molecular beam epitaxy, we were able to grow these superlattice series. So here's the 124 end member and the 113 end member of lutetium ferrite. And this one is epitaxially stabilized. It's not stable in the bolt. And kind of to our surprise, and then here we have the superlattice series in between with M equals 10 single iron layers over here with one 1,2,4 double iron layer in the middle. And here we have the M equals 1, where it's alternating back and forth. And kind of our surprise, or maybe not to our surprise, we've had enhanced critical temperature in these superlattice layers. So here for the 1,2,4 lutetium ferrite, the TC is around 240 Kelvin. This one, TN, around 150. But this M equals 9 superlattice structure had 281 Kelvin, so getting close to room temperature. And so here's the Curie temperature, and the magnetic moment is a function of composition, ranging from the 1,2,4 in member to the 1,1,3 in member. So this 1,1,3 in member is the ferroelectric component. And as you go towards this ferroelectric component, you start getting enhanced TC and enhanced magnetic moment. So what's going on with the polarization in these superlattices? So we go by STEM and we can look at the M equals 1 layer. You can't see very much happening with the distortions here. But as you go to M equals 2, you start to see some ferroelectric rumpling. And M equals 3, it's getting larger. For M equals 4 and M equals 7, this is getting even larger. And then for M equals 9, it's quite clear. And so for this, we analyzed many lutetium atomic columns, over 142,000, to get statistics. And so we saw that the polarization is present for M greater than 2, and it's getting larger for larger M. And so we can compare this on. So here's our TC, or magnetic moment, and then we map the polarization as a function of composition. And we can see that this polarization is going up as our magnetic properties are going up. And this is just what we had thought from the DFT from Craig Feeney's group, where you can tune this Q parameter and get the higher TC. So here, as we're increasing this polarization, we're getting this higher TC. And so the ferroelectric distortion in this crystal is actually reducing the magnetic frustration, enhancing the magnetic TC. So this also shows electric field control of magnetism. So here's ferroelectric polling of the lutetium ferrite superlattice by PFM. So red, I think, is polarization up, and blue is polarization down. And then they took this to the PEAM to measure the magnetic signal on the iron 3 edge and L3 edge. And here you can see that even at 320 Kelvin, you get a magnetic readout, which is mapping what happened with the PFM measurement. And so this is just showing the superlattice has electric field control of the magnetism. But the other thing that we started noticing whenever we were looking at these crystals is that as we increase this layering pattern here, we get this regular ferroelectric domain pattern with larger M. So we're always stabilizing polarization up on the bottom and polarization down on the top of these 1,1,3 lutetium ferrite layers. And so we can do statistics from this, and we can see that the occurrence of tail-to-tail domain walls goes up as we increase the M and the superlattice layering. And as this happens, this is forcing charged ferroelectric domain walls to occur in the 1,1,3 lutetium ferrite layer. So as you increase M, you're getting more and more charged domain walls occurring over these layers, with the neutral fraction of walls, which are neutral, falling off. So this growing this epitaxial superlattice is also stabilizing charged ferroelectric domain walls, which we may be interested in for these domain wall devices. And so what we think is happening here, so this is again DFT from Craig Feeney's group, is that nominally this 1,2,4 double iron layer has an iron valence of 2.5, whereas the 1,1,3 has a nominal iron valence of 3. And so what they calculate is that an electron is moving from this 1,2,4 layer into this 1,1,3 layer, which is then stabilizing the charge buildup for these head-to-head domain walls. And so we can see what happens in these superlattices as a function of M. So when M is large, what happens is we most often get these patterns where we have these stable charged domain walls running through the material. Whenever these charged domain walls sort of terminate at the end here, we get these kind of half vortices. And so what's happening is it ends, And then in order to restabilize the tail-to-tail domain wall that wants to energetically form on this double iron layer, it will terminate abruptly and then restart another polarization up region over here. And so you get these 3 ferroelectric domains coming to a point at that double iron layer. And so this is kind of an unusual structure that you wouldn't necessarily see in the bulk crystals because they always form full 6-fold vortices. So we can see this wrapping in the anti-clockwise and the clockwise directions. We can also see what happens as these kind of come close to each other. So here you can see these may come close across this double iron layer where you can get multiple domains in close proximity. You can also see within this single lutetium ferrite block, the domains, the phase may wind going through in unusual configurations. And then very rarely we may get all of the domains wrapping around a single point. So whenever we confine this further to m equals 4 and m equals 2, here we can see for the m equals 4, we do get regions of charged domain walls, whereas for the m equals 2, this tends to not happen, they tend to be smaller. We also get regions where different numbers of domains may come to a point. So here 4 are coming to a point. And then we can also stabilize these structures where the ferroelectric phase is winding in kind of more of a stripe pattern through the crystal. And so we can look at the ferroelectric order parameter for these materials. So here for the m equals 9 case and the m equals 7 case, we get the 6 distinct ferroelectric wells. For the m equals 1 case, it looks more paraelectric. But sort of interestingly, in the intermediate for the m equals 2 and m equals 3, we kind of get the superposition of different states happening. Here we can kind of see there's not much happening in terms of 6 distinct ferroelectric domain walls. It's sort of rotationally invariant with some density in the middle, whereas here we can get both paraelectric and some ferroelectric domain walls observed. And so we can just plot this out. The fraction of the states which are paraelectric decreases with m, whereas the fraction which are ferroelectric increases. And so this is sort of like changing the critical temperature by changing the confinement, as we've heard about earlier. So with that, I want to conclude and take any questions.
Yeah. Thank you for the talk. Very beautiful images. I was wondering if this double layer of iron that you have in different superlattices, can you comment about if there is some kind of charge ordering there and if it evolves with M?
We did look for charge ordering with eels, but we were never able to see it in those structures experimentally, at least. So we're assuming that the ferroelectricity in these superlattices is all coming from the 113 ferroelectricity.
Okay.
Yeah.
Okay.
Yeah.
Other questions?
So you talked about at the beginning when you applied a voltage to the charge domain walls. I didn't quite catch what was happening though. Even in the case of the head-to-head and tail-to-tail domain walls, you got charge accumulation at the walls.
Right. So there should be charge accumulation at the walls. When you're applying a large enough voltage, it crosses over into a different, you're like dumping too many electrons into the wall and you get a different conduction mechanism, if that makes sense. Yeah.
Do the charge domain walls make it difficult to switch?
So we were hoping that the charge domain walls would be the conduction pathway because the bulk of the material is insulating. So ideally, if you're going to make a charged ferroelectric domain wall device, you would be able to control the placement of those walls and then use single walls to switch.
No, I meant to switch the whole material.
Oh, yeah. So are you talking about the superlattices or the bulk crystal?
But just in general.
Yeah, so when you switch them, it just, the walls which are of the polarization, which is not preferred, shrink down. And those they're like topologically protected, so they're still there. And then whenever you switch the other way, this relative size changes. Yeah.
Maybe I misunderstood completely, but if the charge domain walls come from the different balances of your iron atoms, with respect to the average iron balance, let's say, they do not need to be metallic, right? I mean, they could be perfectly be insulating, which would be consistent with the fact that you are able to write domains.
Yeah, so we think that they're not metallic because we're able to switch it.
Yeah,
so in the lutetium ferrite case, we think they're probably not going
even
metallic,
the statement, that you expect charge accumulation at the domain walls is not trivial, right? I mean, in principle, that doesn't need to happen.
Yeah, absolutely. Yeah.
So if there are no more, let's thank the speaker again.